Hi, good morning, good evening, and good afternoon, everybody. So today we are going to discuss about the IPSec VPNs. So we will see the different message types. There are, six messages that being exchanged between the initiator and the responder, and we will go through every single message. And with the help of Wireshark, we will see that what all the messages and what are the key details that's being exchanged between the sender and the receiver. And we have and followed by that, when we are doing troubleshooting, we'll see what if the phase one is up. Phase one is your ISACamp tunnel, that's your actual encrypted tunnel, and the phase two is your IP traffic that is encrypted, that is phase two. So we'll see what if phase one is up but the phase one is down. So now how we are going to troubleshoot, and what are the key troubleshooting steps we have to follow to figure out on why phase two is down. And followed by that, phase one is up and the phase two is up. Your ISACamp tunnel is up and your IPSec tunnel is up. Both the tunnels are up, but the traffic is not flowing between the source and the destination. So how to troubleshoot that scenario? We have to look for the routes. So if you still have your phase one and phase two up and still something is blocking, we'll look for, is there any particular ports are blocking, or what kind of traffic is that? And followed by that, we'll see how this private IP to private IP communication is happening. This is generally your, this is actually your interesting traffic. So from this source to the remote network, so what is the exact subnet that's being allowed to talk inside your tunnel? So, and followed by that, if you really have time, and then we will look into the NAT configuration. So the main focus is the complete IPSec tunnel with all the messages. Followed by that, we will look into how we can create an aggressive mode. Aggressive mode is not, I would say in few use cases, they use aggressive modes like your remote access VPN. But for the site-to-site VPN, it is always we use main mode, because we know in the aggressive mode, the actual key exchange, the Diffie-Hellman key exchange, right? That actually shared between the sender and the receiver. So it is the hash is a clear text. So somebody is doing a man-in-the-middle attack, and they can see the passwords. So aggressive mode is not very secure, but it is still implemented for remote access deployment. But for the site-to-site tunnel, we'll be going to do the main mode. And then we'll talk about what is ISACamp framework, what is IKE phase one, IKE phase two, what is asymmetric encryption, what is RSA algorithm, and what is a Diffie-Hellman group. And we'll see what is IKE exchange modes. What is main mode, what is quick mode. The quick mode is for your IPSec tunnel. Yep. And the aggressive mode, and I missed one more thing about the aggressive mode. So your 6 messages is squeezed into 3 messages. That's a bit quicker, but actually, technically, you don't actually see the difference in the speed. And the quick mode, that is a perfect forward secrecy. We will see what is perfect forward secrecy, what is the key used. This is generally, if you want to give a very quick insight about what is PFS, when we do a IKE phase one tunnel, we are actually using the Diffie-Hellman group on the IKE phase one. In the phase two tunnel, actually, we are just using the key which is created in your phase one tunnel. So your actual tunnel is a phase one, and the in the phase two you have an encryption and hashing, but your actual tunnel is your phase one. Your traffic is going through your IKE phase one. So if you really want your Diffie-Hellman key to be created for more security, that is perfect forward secrecy, you can do that. But in the most implementation, we just rely on IKE phase one key, the Diffie-Hellman key created in the phase one. that is actually used to carry your actual session keys between your source and destination. And coming back to the IPsec modes, there are two modes. The tunnel mode is the end-to-end encryption. We know from the end computer to the remote end computer. It's from the endpoint to endpoint, the complete encryption happens with the tunnel mode. So the most preferred deployment for IPsec tunnel is IPsec tunnel mode. And in the IPsec protocols, when we talk about the protocols, it is using its own transport for sending the traffic back and forth. So AH has little bit of vulnerability with AH authentication header. ESP stands for encapsulation security payload. So the most used or encapsulation security payload, because in the EAH still we have few messages that they are not encrypted. So from the security standpoint, the most of the deployment that happens in ESP, and if I am not wrong, in my understanding, the FortiGate firewalls, they don't use AH. It supports only ESP. So the ESP is most widely used protocol for IPsec tunnel configuration. And we'll see if you create an IPsec tunnel, and if you want to make your communication to the remote network, and what if both the LAN segment are in the same network range? So how do we overcome the problem if you want to build a tunnel with a remote destination F, and if both the LAN IP range falls into the same subnet, so that's called as an overlapping subnet. So how do we overcome this with IPsec, and what are the implementation best practices to overcome this problem? So we will see that. So to start with, let me give you a quick insight about the ISACAM framework. As I said, the whiteboard, the whiteboard teaching is furthermore reduced, as I said. I'm not going to take much time with that. I'm going to just give you a glimpse about what are the messages, and just want to give you a more visual about that. So right away you jump into the packets. It's pretty hard to to visualize, to picture the whole process. So I'm not going to take much time with that. So very quickly we'll go with this. So if you look at this, this is a visual representation of a tunnel. So we got two phases. The first phase is called ISACAMP, Internet Security Key Exchange. IKE phase 1. This is called ISACAMP protocol is used for your first tunnel. There is no actual IP traffic is going through that. So if you actually see this, your primary tunnel is ISACAMP, and your IPsec tunnel is going through your IPsec. Sorry, it is going through your ISACAMP tunnel. So your primary tunnel is ISACAMP, and your IPsec tunnel is going through your ISACAMP tunnel. So the protocol used for this, it's UDP 500. You have to ensure that the UDP port 500 is opened for your actual control plane traffic. And your actual data plane traffic, if you see your data plane traffic, this UDP 500 is used for all your negotiation phases. If you say this is phase 1, we say it is an HADLE. I'll come back to that. The HADLE, what is HADLE process in the IKE phase 1? So for the phase 1, your UDP port 500 should be opened for your successful authentication should happen. Then the UDP port 500 should be opened on both ends. And your actual data plane traffic, if I say data plane traffic, your actual IP communication happens over your ESP tunnel. That is your phase 2 tunnel. So as you see the traffic, even in the ISACAMP in the beginning, when the key packets, it's being exchanged between the source and destination, you can see the packet until MM4 for fourth message, because that is again until message 4, it is just sharing the key. The session key is being shared, so that is not encrypted. So after the fourth messages, the fifth and sixth messages are completely encrypted, because you don't see anything. So that's when your actual tunnel establish between your source and destination. And if your ESP, if you look at that, everything is encrypted because it is completely going through your ISACAM tunnel. So your complete traffic is encrypted in your IPsec. So say for example, if you do a ping and if you try to open the payload, you don't see anything because everything is encrypted because this traffic is again going through your ISACAM tunnel. So when we are troubleshooting, it is always you have to ensure that your ISACAM tunnel is established. Only then you have to move for your phase 2. That is the actual troubleshooting and the best practice to deploy your IPsec tunnels. So coming back to that, I mean, the very key thing here we have to understand is we call this as an HADLE. So let me take a pen very quickly. I'll explain this. 1 minute, guys. I'm connecting my pen. So, for example, I got 2 routers. So I got 2 routers over here, and just I have an ISP in the middle. So I'm going to establish a connection. So what is the very first information? I mean, I would say what are the key values when I'm trying to establish a IPsec tunnel? So what are the key information I should know about? So this is purely a phase 1, what we are talking about, this HADLE. So we will be using hashing. Don't worry about that. We will do this in practical. You will understand better. So I'm just giving a quick insight about that. So this is your initiator. I stands for initiator. R stands for responder. So both the source and destination both has to agree on all the parameters. What is being exchanged between the source and destination. So we'll be using the hashing. That is for data integrity. So the data is not tampered and it is sent across perfectly without any tampering. It is reaching the destination, or and then followed by that the authentication. So there are 2 ways we generally use, but we are using a pre-shared key because the digital certificate implementation is pretty complex. So the most widely used practices is to use your pre-shared key for it. And your Diffie-Hellman key is actually your actual key. I'll tell you. Diffie-Hellman is, example, I'll draw a key here. So example, this is a Diffie-Hellman key. So, this is actually the Diffie-Hellman key is responsible to create your session keys because your sessions should never be hijacked. So Diffie-Hellman key is the key that is used for your session. So what is the use of pre-shared key then? So the pre-shared key, if you look at this DH key, this is your session key. And actually the purpose of the pre-shared key, right? It is to carry the Diffie-Hellman key from source to destination. So nobody can use it, right? So if I have a session key, who is actually the legitimate user in the other end who can use the same key? So he should also use the same pre-shared key to use this Diffie-Hellman session key. So we'll do that practically. You will understand better again. So the lifetime is how long this should be active. So if most of the time, if you see your state should be main mode state will be idle state. You know why? Because once the key is created, it keeps generating your session keys. But whenever your session key expires, it creates a new key. Until that, your state will be in idle state, right? And most of the time, if you see, if you give show crypto ISACAM SA, your state will be idle state. At that point, you have your key created on both end because it's just a shared key. Both end they create a shared secret key and it is being exchanged. And if it is an expired, until then the state will be an idle state. So that is called the lifetime. So how long does the IKE phase 1 tunnel should be stand up? The shorter the lifetime, the more secure. Because it rebuilds the new key. So every vendor has a different lifetime, but the general practice is always, to give 1 day. And the encryption, how we are encrypting, so you're using the DES, 3DES or AES. So AES is more powerful and most preferred. So this is called an HADLE. So to build a tunnel, these 5 parameters are very important. Okay, so here is your tunnel going in. So this is your source and this is your destination. So I'm going to create 2 tunnels. This is phase 1 and this is phase 2. So we talked about HADLE. So let me come back to the phase 2. So this is your phase 1, right? So both end it's an HADLE connection. So to build your phase 1 tunnel, you need all this key material. Your hashing, your authentication, Diffie-Hellman key, your lifetime, how long the tunnel should be up and running, and your encryption. So from the source and destination, it should match. I cannot use SHA-256 over here, and I cannot use SHA-512 here. So your all the 5 key materials, it should match exactly the same on both ends for your successful phase 1 connection. And along with that, I mean, we will be using your pre-shared key or certificate. As I said, the most widely used deployment is your pre-shared key. So this pre-shared key is actually the pre-shared key is actually whatever the Diffie-Hellman key that is created for your session, right? On both ends, the Diffie-Hellman key here. So the private key is responsible to carry this Diffie-Hellman key, wrap this with pre-shared key, and this will send it across between source and destination. So the actual job of pre-shared key is to carry your Diffie-Hellman key between your source and destination. So this is really about phase 1 tunnel. And when we talk about the phase 2 tunnel, here is actually your ESP is used, ESP protocol. So we will be using your transform set. We are just creating your hashing plus encryption. We are not creating any key because we make use of phase 1. The Diffie-Hellman key is used to encrypt the traffic. So in the phase 2, only your IP traffic, right? your data plane traffic is going through your phase 2. So if you actually see this, so this is your phase 1. So phase 2 is going through your phase 2 is actually going through your phase 1 tunnel. So I'm going to use the same Diffie-Hellman key for my session. So I'm going to use hashing and encryption only for my IP traffic. So that's the reason we are using a transform set. And finally, only the three, the three steps are very, very important. And I would say the three steps are very much important to create your tunnels. So this is something you should understand better. Phase 1, your HADLE, your hashing, authentication, Diffie-Hellman, lifetime, and encryption. And this is your IKE tunnel, IKE phase 1. Your IKE phase 2 is ESP protocol is used. I should write here. ESP protocol is used here, and the protocol number is 50. So here, what are the key values you configure in the device for it? Your transform set. So what do you have inside your transform set? Your encryption. Example, I am telling you this is AES 256 plus your hashing. You can do your MD5 or your SHA. 512 example. I'm talking about the source and destination. Both should have it. Both source and destination. Phase 1, phase 2, key materials, and the phase 3. I'm not saying, sorry for that. Not phase 3, we got only 2 phases. And the third step, what we have to do to establish your IPSec tunnel, that is your crypto map. And the fourth thing, you have to apply on your egress interface, or maybe the interface with your public IP address. So your main mode happens on phase 1, and your quick mode QM happens on your phase 2 tunnel, and the crypto map is actually your binding, right? So you're binding everything in your crypto map, and you're going to apply in your interface, egress interface, your actual device that is connected to the internet. So you have to follow only these 4 steps to create your IPsec tunnel. So now let's jump back to the lab. And then let me give you a little background about IPsec tunnel. So we all know this; it's quite familiar. So we are sending this traffic without IPsec tunnel; it is not encrypted. So IPsec tunnel is mainly that innovation of IPsec tunnel is to secure your connection, because I mean, maybe back in 80s, and back in, I mean, if I say 80s, maybe 40, 50 years back. I mean, mostly we used MPLS because it's a separate private cloud. You have to pay a lot for it. But the VPN is a best cost-effective solution. Even your traffic is, even if you want to route your traffic over the internet, but still it is secure because we are encrypting the traffic. So that's the main objective of it. So imagine here R3 and R1. I mean, this is something I just defined this as a branch office devices, and this is a hub here. So I build a tunnel between the R3 and R1 right over here, the R3 and R1. I build a tunnel over R5 and it's going to R3. R5 is your hub. So we are going to do a IPsec tunnel between R3 and R1. Let me, before doing the lab, I mean, I want to give you more, little bit insight about what we discussed. We'll see this from the configuration standpoint, how it looks. Let me open the console. So I am on R1, as I said, to build a tunnel, show run section, ISACAMP. If you see this three values. So very first thing, the policy is dynamic. So I'm going to tell that I'm to create a ISACAMP tunnel, the phase one tunnel here. I mean, let me write this. So if you look at this, this is your phase one. So we discussed about HADLE, right? So H stands for hashing. So we are using SHA-256. So authentication, if you see this authentication, we are using a pre-shared key. This is D. So we are using hashing, we are using authentication is a pre-shared key. If you look at this, my pre-shared key is this guy. Cisco is my pre-shared key. So I'm using an aggressive mode here. So I'll come back to that in detail. But right now we are just discussing about the handle. So the Diffie-Hellman is a group. If you see the group 2, this is Diffie-Hellman. As I said, this is used for your shared secret between your source and destination. And in the phase one, you will define your what is your the peer, your public IP address. So this guy right over here, he is this guy right over here is 50001. So I am making a tunnel from this guy. So for him, for R3, my peer is I'll go back to R3 and I'll show you that. So if you look at this, this is the destination here, right over here, this guy. So HADLE. So as I said, it is hashing, authentication, Diffie-Hellman, your lifetime, and your encryption. If I'm not defining the lifetime, then it takes the default. We'll see that in Wireshark how it looks. So to build a phase one tunnel, all I need is my HADLE. You can see this right from here to this, my pre-shared key, my peer, Diffie-Hellman. Diffie-Hellman is defined by group 2. Sorry, I mean the group, the If you have a higher group number, the more secure it is. So I'm using the middle value group 2, encryption, hashing, authentication, and Diffie-Hellman. So this builds my phase 1 tunnel. So coming back to the phase 2 tunnel, this is an aggressive mode. We will do the a proper main mode configuration, then we will do this aggressive mode. And I'll show you that. When I'm doing that, I'll show you the key materials used for phase 1 in main mode. So this is actually we are trying to build the phase 1 tunnel in the aggressive mode here. So all I need to do is just an HADLE. That's it. So here, if you look at this, I am binding my phase 2 tunnel with phase 1 tunnel in the crypto map. And I'm going to define my peer in the phase 2. And I'm going to use my transform set to bind. And followed by that, I have to define my interesting traffic. Between my R3 and R2, what is the interesting traffic? If I see show IP access list, 100. So this is my interesting traffic. So only the IPs 1.1.1 and 3.3.3 can communicate over this tunnel, not any other IPs. That's the whole meaning of this. So now let's see in the Wireshark capture how the packets looks, the Wireshark perspective. So we are not right away jumping into the aggressive mode. We'll go from the main mode. But here I'll show you how it looks here. So if you look at this here, as I say, the HADLE, the hashing algorithm we are using is SHA. H stands for, in the HADLE parameter, the H is for hashing. A for authentication. Authentication is we are using a pre-shared key. And if you see, this lifetime is 86,400 seconds. And the key length is 256. And the encryption is my AES encryption. And the lifetime. Yeah. So I got my HADLE here. So the same thing I should see on the remote destination. And who is sending this HADLE information? How do I check that? All you have to do is you have to go to your source IP address. So 60.0.0.1. If I go back here, this guy here is 60. If you look at the 60.00/24, this is dot one and this is dot two. This guy R1 is 60.0.0.1. So he is proposing all this handle information to the destination. That's the meaning of it. So the same thing the other guy on the other side, right? From 50001, I should see the same handle information to establish my phase 1 tunnel. Once I build the phase 1 tunnel, your ESP is your phase 2 tunnel. And if you see what is inside the phase 2 tunnel, and then I missed to explain one thing about the ESP. I'll come back to that. So here, if you actually see, you can see two IP address that is actually used. From the ESP standpoint, I'm telling from the ESP standpoint, this is called an outer header because this is not encrypted because this is for your actual routing because 60.0.0.1 is talking to 50.0.0.1. Your communication is happening between R1 and R3 over the public IP address. And but the new header, right? Your source and destination. If you look at this, here the actual source and destination is 60.0.0.1 and 50.0.0.1. But this is encrypted inside the ESP. If you look at this, this is an ESP. Inside the ESP, my so private IP address are encrypted, so nobody can see it, and it is not routable. So why it is not encrypted? Why ESP is most widely used? Because the outer header is not encrypted. So I'll draw this for better understanding. So in the ESP, I'll show you the header value there. In the ESP, the outer header, your public IP address, this is your outer header. So in the my outer header is 60001 and 50001, right? This is my outer header. This is not encrypted. But my private IP, right? So that is my 1.1.1.1 to 3.3.3.3. This is encrypted. So this is a new header created when you create a ESP tunnel, your phase 2 tunnel. When you create your phase 2 tunnel, a new IP header is created. So inside that, you have your actual private IP address. This should be encrypted because this is not routed. So the routing happens purely based on your outer header. So when you're doing a Wireshark, you should look into all these options and you'll understand this better. So if you look at this, this is a source and destination here. This is my source and this is my destination. This is my private. And this is my outer header. So when most, I mean, in my, I mean, when we deployed multiple DMVPN tunnels, we never do natting because of this. Because only your outer header is actually your routing happens based on your outer header when you do an IPsec tunnel. So only the traffic which is going to the internet, there you might be using your NAT configuration. But when you actually create your IPsec tunnels right over here, example, you have your hub and this is your spoke. You have a connection like this, and this is your source and this is your destination. And you build a IPsec tunnel between these two guys, right? This is an R1, this is an R2, this is an R3. So you don't want to really do a natting when you're doing an IPsec because your outer header is actually used for routing. The new header, right? Whatever it's created inside your ESP tunnel, that is encrypted. So what happens here when the traffic goes from this guy R3 to R1, right? So when it reaches, so it decrypts the traffic, the R1 decrypts the traffic and it opens the header, my private IP address after decryption. So this is how the whole process of IPsec tunnel, this is how exactly happening. So you have to find a difference between what is ESP and what is ISACAM. And very quickly, let's jump back to the slide and we'll just go through two things here. So now I think you guys can understand better. So this is your ESP tunnel mode. So this is your original IP packet. But when it is going to your ESP tunnel mode, you look at this, your actual IP header is encrypted here. Your data payload and the ESP and the whole thing is authenticated here. And if you look at this, the right over here, this particular packet, your new IP header, the one which I am talking about, this is your new IP header, right? If you see this, this is encrypted. So here is actually your private IP address. This new IP header is for your outer header that is used for your routing. So since this is an encrypted, so nobody can see your private IP address. So your actual public to public IP address is communicating between your source and destination. So the routing is happening based on your new IP header. And once it is successfully decrypted on the destination, it can see your private IP details inside. And the same thing happens back and forth. So see this is where we use a new IP header which is useful for site-to-site VPN. So now let's jump into the lab and let's start doing the configuration. So the very first command to check from I'm on R1, so how do I check is my phase 1 tunnel is up. Show crypto ISACamp essay. If you give the detail command, you can see your HADLE information. Your hashing, SHA-256, authentication pre-shared key, Diffie-Hellman, your lifetime, and your encryption. All your HADLE value. HADLE. So this says it is local. This guy 60001 right over here. If you see, this is 60001, and the remote destination is 50.0.0.1. So this is IPv4 crypto ISACamp SA security association. All this information should be same on both ends. So now let's delete this and we will build the tunnel again. And let me show you the phase 2 tunnel also for you, the ESP tunnel, show crypto, IPSec SA, IP security, layer 3 encryption. And I want to tell you one more thing, very important. So your whole communication, when it comes to the interview standpoint, they ask this question: what is SPI value? There is an unique value that is used by the source and destination. So if I say my inbound SPI, go to the Wireshark, I think I have to open it. Where is my addressee mode? Okay. So if you look at this SPA value, right? Let's try to match this. The BA80. If I say inbound, I am on R1. So the SPI value of this particular device, right? I mean, I would not say this particular tunnel. I'm sorry for that. For this particular tunnel, the IPSec tunnel, my inbound is my SPI value of this particular tunnel from the source, 60001. This guy, right? Local endpoint. So this is the value associated for this. We'll do this in the lab and you will see that. My outbound SPI is my remote SPI right over here. That's how you will differentiate your main mode exchanges. You can differentiate who is sending this HADLE information, who is proposing it. So your SPI value is very important to understand who is sending that actual traffic. And if you see this in the transform set, I am using the null encryption and I am using the SHA-256 HMAC. This algorithm used in my transform set. As I said, we are just using encryption and hashing and the session keys and the key creation, everything it is happening on the phase one, not in the phase two. If you see this, the Diffie-Hellman group is none. So we are not doing a Diffie-Hellman key exchange in the phase two. We are doing only this on the phase one. But as I said, if you want to use perfect forward secrecy, then your Diffie-Hellman group is enabled here. If you see this PFS, is no, we are not using a Diffie-Hellman here. If you use your Diffie-Hellman, this will be your option will be you should see something S here. But here, as I said, we are using the Diffie-Hellman. Only the key exchange is happening in the phase one, not in the phase two. And what are the key values I should see inside? So it is on Ethernet 0/0. If you look at this, this is on Ethernet 0/0. So I created this. The crypto name is Cisco, and the local address is 60.0.0.1, and my peer is 50.0.0.1, and this is using UDP 500. And what are the interesting traffic inside my phase two? It's 1.1.1. This guy, if you see the router ID 1.1.1 and 3.3.3 is right over here. So it's happening between these two. The interesting traffic is only 1.1.1 and 3.3.3. And you can see your packet encryption. It is happening on the source here. This guy is encrypting with all the HADLE information, and the decryption exactly happens that traffic coming from 3.3.3, it is doing a decryption. So you should see your both encryption and decryption happening on both ends. And you know what, in most of the cases, if your phase one and phase two both are up and if still your traffic is not encrypted and decrypted, it could be a problem with your routing most of the cases. If you don't have an inbound, I mean, if you do not have a return route, then your decryption will not happen because you are encrypting your traffic. You're encrypting your traffic and you're sending this to this guy. But what if this guy doesn't know how to reach you? So then your decryption will never happen here. From the troubleshooting standpoint, you have to look for all these values. And what about the session? How do you check your session? Show crypto session. If you actually, you should always, you should see this should never be in idle state. And if you see show crypto ISACAMP SA, as I said, this is an idle state. Why is that? Most of them they'll ask a question. So so it became in the quick mode, it is an idle state because the session key is created. It's being used. After the lifetime, the new key is created. Until that, this will be in a sleeping mode. But if you actually see the phase two tunnel, show crypto session. Yes, your IPSec tunnel, the source and destination is this guy, and your session status is an up and active. It should be always up and active. So we should use these three commands. Maybe the vendor, it differs. You have to check your crypto session, your active session status, it will show you. Then you have to check your phase two tunnel, all the key parameters as I said. And in the phase one, you have to check your state. It should be quick mode idle state. And when you're troubleshooting and when you have a problem with your tunnel one creation, you should run this command on both devices. You have to check your security. Sorry, you should check your You should check your HADLE information. Both ends should have the same thing. If you look at this, I am on R1. The encryption is AES, SHA, PSK, Diffie element group 2. The lifetime is 8,300 seconds. So if I jump back to R3, show crypto, ISACAMP, SA. So you can see the same encryption AES, SHA-256 pre-shared key, and the Diffie element group 2. So this is important, very important for your phase 1 tunnel. That's it. So we will clear this and we will do the configuration. We'll build the tunnel and we'll see what happens and what are the key information it's being exchanged between source and destination. Show run section, ISACAMP. So when I'm doing that, I'll tell you one more thing here about the policies. The policy number is not necessarily should match on both ends. It is purely based on your handle information. The policy number is locally significant, so that's not going to impact anything. So I'm going to remove this policy from R1. And if you see the um, show crypto ISACAMP SA, show run section ISACAMP. Show run section ISACAMP. So I deleted all the config. I'm going to remove the crypto map. As I said, in the crypto map, you're actually stitching your IPSec and ISACAMP tunnel phase 1 and phase 2. So we have to remove the crypto map from the interface first. Show run because it's binded Ethernet 0/0 config interface Ethernet 0/0. No crypto map Cisco. So then I'll go back to this config. You see, it went to no state. Let me jump back to this R3 show run section. ISACAMP config. Let's do this pretty quick. Deleted this. Going to delete my peer. So before that, I have to remove the crypto map from the actual interface. Show run interface Ethernet 0/1 config. No crypto map Cisco. And then I have to create the crypto map. Sorry, I have to delete the crypto map. So if I give show crypto ISACAMP SA no state, it's deleted. It's the detail I don't see anything here. Encryption, hashing, thing, show run, section, ISA camp, so show crypto session. If you see show crypto session, I don't see any session right over here. Nothing. It's blank. Show crypto IPSec essay. No essay found. So your phase one tunnel is not up. Then the ESP cannot communicate if your phase one is down. So let's quickly do the config. So I'm on R3 right over here. This guy. I'm doing the config on R3. Crypto ISACamp policy 10. So I'm creating a policy now, and I'm going to define my encryption. In my HADLE, I'm doing my encryption. Encryption A is 256. Then my hashing, I'm using hashing SHA 256. SHA 256. Authentication pre-shat key. I'm using Diffie-Hellman group 2. You see this, you can see this. This is this Diffie-Hellman, and I'm using a group 2, 1024 bytes of data. My key length is 1024. Group 2. And then I'm on R3. So my peer is my public IP address peer is 50.0.0.1 right over here. So I have to define my crypto ISACamp key. I'm using a preset key in my handle, so that's Cisco, and the address is 60.0.0.1. From this guy, my peer, the outer IP, if you look at this, 60.0.0/24 is my external IP address, and .1 is used. So I'm going to use this IP address right over here. I'm going to make a peering from R3 to R1, and the public IP address is 60.0.0.1 in my topology. 60.0.0.1. So my phase one is done. So I'm going to do a phase two. How do I know it's a phase two? It's IPSec tunnel, crypto IPSec transform set. As I said, I'm going to give a name for it. If you give a question mark, it is just a name. So I'm going to give Cisco as a name. And I'm going to use my encryption to do this contextual help. You'll see this. So I'm going to use the ESP null encryption. And I'm using the hashing SHA 256. And I created a phase one, I created a phase two. Now I'm moving to the crypto map. Crypto map, I'm going to give the same name Cisco, and I'm going to give a sequence number for it like an ACL. And I'll talk about that when you're creating multiple tunnel to the destination, you will make use of this. I'll come back to that. So we created a crypto map, and I'm giving a name for it and the sequence number. Now I'm stitching my phase two and phase one tunnel together in my crypto map. So until you configure your peer, this remains disabled. So set peer 60001, my R3 public IP address and set transform set. The transform set what we created here, the Cisco. So I'm going to map this in the crypto map. And I want to match an IP address. I mean, let me see, do show IPs access list. So it's an access list number 100. So I'm going to match this match address 100. Show crypto ISAC campus A. Because the security association is not happening because I haven't configured this on the other end. Let's jump back to R1 config. I'm on R1 this guy. Crypto ISACamp policy 10 in, encryption AES 256 hashing SHA 256. It should match on both ends. Authentication pre-shared key. This key is actually carrying my DFI element session keys. Group 2, the key what I'm creating here, the pre-shared key is actually taking encrypting this traffic and taking this to the other destination. So nobody can use it other than who has the same pre-shared key on the other end. That's the whole purpose of this. The group 2, I finished this config ISACamp policy. So crypto ISACamp, I'm going to use my key, pre-shared key, and my address 50001 because from R1 my destination is 50001 right over here. This router 83.3.3, the public IP address is 50.0.0.1. You can see this right over here, 50001. So now I'm going for phase 2 tunnel, crypto IPSec transform set. I'm giving a name for it. Same encryption, null encryption using ESP. ESP stands for encryption security payload, phase 2 tunnel. So I'm going to use SHA-256 HMAC. Then I finish the phase 2 tunnel and I'm going to do a crypto map binding the phase 1 and phase 2 crypto map. I'm giving a name, same name. It can be different, no problem. I'm giving the same name. Sequence number 10. Then I'm stitching my IPsec with phase 1, phase 2, and phase 1. Both are stitched together. Set my peer. From this guy, the outer header is 50001. So my peer is 50001. Set, transform set. Cisco. I use the same transform set. If you see here, my transform set is Cisco. So I'm switching this transform set, the crypto map. So this is basically you're mapping out your phase 1 and phase 2. Exactly here. Your ISACamp, all your HADLE information, and in your IPsec, you have your authentication and hashing. Both are stitched together. And do show IP access list. So I'm going to use an access list 101. I'm going to, okay, sorry, I'm going to use an access list 100, the interesting traffic between 1.1 and 3.3.3. So my matching address would be match address 100, the ACL number, if you see this one, ACL 100. So crypto is a campus C. I don't see an association still. Show run section route. So from R1, if I want to reach 3.3.3, I'm going to 60.0.0.2. Okay. So let me do debug crypto. I have to start with my phase one. Uh, can anybody know the answer why the negotiation is not happening? Let me know in the chat. You guys know the answer. Show IP interface brief. Show IP interface brief. Exclude unassigned. I'm on R1. Ethernet 0/0 is my external interface, and I haven't configured my crypto map on the interface. Only then your negotiation starts between the source and destination. So I have to do a crypto map. Let's go. So if you see this, once I enable this, the ISACAMP message is turned on. If I go back to this guy, R3, show IP. Now I'm on the top router R3. Show IP interface brief. Include unassigned. Show run interface. Ethernet 0/1. Config. Interface Ethernet 0/1. Crypto map. Let's go. ISACAMP is on. Show crypto camp SA. Can see the phase one is up. So when you're creating, as I said, you should never forget to enable your crypto map on the interface. Show crypto IPSec SA. I can see the packets encapsulation, decapsulation happening. And how do we see this in the Wireshark? Let me generate some traffic. So show crypto session, the command to check. If you see this, an up and active. Let me go to an R1. If you see the messages, we'll come back to that. The messages one by one. I'll give you all. So you should generally see 6 messages exchanged. Okay, let's start from here. So I am on R1 right over here. This guy, R1 right over here. So there are totally 6 messages being exchanged, right from main mode 1 to main mode 6. So I'll tell you in the Wireshark, we'll see this better than this. Let me do a Wireshark capture for it. So let's quickly do an encryption decryption testing one more time. Show crypto IPSec SA. So packet encapsulating decapsulation happening. So my routing is happening, correct? If you don't have your route, you can't see your encryption decryption happening. So if I give ping 3.3.3 from R1 to R3, route ready 3.3.3, my source 1.1.1, repeat 100. I'm sending some ICMP packets. So crypto, IPSec, the same. You see this, my encapsulation, decapsulation packet is increasing. Let me do it one more time. So I have to do same testing on the R3. Ping 1.1.1, source 3.3.3, repeat 100, show crypto, IPSec SE, and you can see the packet encapsulation and decapsulation happening. Should happen, both encryption and decryption both should happen. So let's do a capture now. So your actual traffic, your IP communication is happening. Your IP traffic is going through your IPsec tunnel. So let me open a capture on this guy. Capture Ethernet 0/1. So as I said, okay, let's go from phase one. That would be better. Instead of this. Yeah, from phase one, I can show you the SPI. So to do that, let me clear the session, clear crypto session. You want to see all your packets right from your phase one. Have to give clear crypto session. Both end R1, clear crypto session. Go crypto ISA campus. You see this, this is deleted. I see the packets right over here. Yeah, I can see the traffic. If I give my ISA camp, the camp packets. So you can see, oh, main mode, okay. So totally we should see 6 messages. We can capture only 3. Clear crypto session. Okay. About. Okay. So let's start from this. So this is an IKE phase one. So the protocol is this ISACAM. So if you see this, the initiator SPI, right? The initiator SPI is, if I go back to this and I'll show you my initiator IS. Okay. Config. So crypto IPSec. Minimize this a bit. Okay. So the responder. So who is the responder? So the initiator is this guy. The responder is, if you look at this value, 0063, is it different here? Show crypto. IPSec. So this is 63. Let me go back to R3. Show crypto. IPSec. 5A1. I think the session changed. So I'm on R3. R3 current peer is 60001, and I'm on the R3 initiator SPI. Okay. Go back to this. EAD1 showing a different SPI value. A1. Let me clear the session one more time. Clear crypto. Let me close this capture and let's do a capture again. We want to capture the SPI values. So I'm going to do a capture on R3, Ethernet 0/1. So let me do an ISACAM packet. And R3 clear crypto ISACAM. SA. Clear crypto session. Going to R1. Clear crypto session. Okay. So let's see. So I should receive 3 more packets. So, okay. It's a bit slow. Now we got it. Show crypto. IPSec SA. So I'm coming from R1 is my 63001 and my inbound initiator SPI. Keep changing it. So my traffic is coming from this guy, right? Okay. Let me go to this 8976. I'm on R1. Okay. 976. Why can't I see my SPI? Okay, got it. So I think I'm looking for wrong value here. Okay. So 3058 0F8. That find 30F8. F8. How come I cannot see my ESP packet coming from 1.1.1? I am on router 1. I should see this SPI for sure. 0x615, 0x615. Clear crypto, IPSec, clear crypto session. Clear crypto session. Okay, so right over here. If you see this, this is from R1. The R1 started the main mode message one. If you see this, the responder SPI, it haven't started negotiating with this HADLE information. So I shared my HADLE information right over here in the main mode. If you see all this HADLE information, my hashing, my encryption. So until this point, the responder is not sending any SPI value. The SPI value is an unique ID to find who is sending the traffic. So crypto session. So crypto IPSec SA. I know for some reason. Okay. Okay, we'll continue this. I'll come back to this for sure. So the SPA values actually it should for every tunnel it maintains the SPA value. So that is an unique number that is used between source and destination. And at this point, this is an the first message. I mean the MM1 and MM2, the both messages are generally they're exchanging the haggle information between both, and both should match. And until this point your packets are not encrypted. You can see all this information when you see the information back here. You can see your initiator and SPI. So who is sending this traffic is 60.0.0.1, and so the destination 50.0.0.1. And also we have to do a capture on the destination to see what is happening there. So let me take this. So mm1 is a message. So it sends all your handle information from the sender, and the mm2 message is the same handle information. If I say handle, we all discussed more about that. So both sends and handle information, and both are not encrypted. And main mode 3 message from the initiator, they send. This is a responder. So message 3 and message 4, they are going for a session key creation using Diffie-Hellman key exchange. They create a shared secret based on all the key materials, all this handle information. They exchange this information, 3 and 4, and message 5 and 6, both are encrypted. So this is a question they ask you in the main mode. So when in the main mode the exchange happens, it shares the handle information and the SPI value of the sender. The SPI value of the sender and the receiver both are different. So again, MM1 handle information proposing for IKE 1, phase 1, sender, and the handle information from the receiver, the same handle information, both should append running. So that's when your phase 1 is trying to negotiate. If you see an MM1 message and if you don't receive the MM2 message, then your security association is not happening between the source and destination. And see, if you see successfully your MM1 and MM2 message, your MM3 and MM4 is actually it is going through your Diffie element key for your session key. So until this point, this is not encrypted. From message 5, they are purely encrypted. Message 5 and message 6 are encrypted. If you see right over this message, this is completely encrypted. This is MM6 message. If you look at this, this is telling that there is a key exchange happening. They are called as nonce messages. When somebody is asking you nonce messages, that is actually your key exchange happening here. You can see this key exchange data. If you see this is MM1 message. You can see all your key materials, your handle messages. So there are 6 messages, as I said. MM1 message from the source, MM2 message from the responder. So those I mean both sends the HADLE information proposal. If both matches, only then your Diffie-Hellman key creation happens between the MM3 and MM4 source and destination. So both key exchange happening, both agree upon the key, and the MM5 and 6 messages are completely encrypted. You cannot see any kind of information on it. You see this? This is a nonce messages, key exchanges happening, MM5, sorry, MM4, and this is an MM5 and 6. If you see, this is completely encrypted. You don't see any information. At this point, the key material is used and your Diffie-Hellman key is created for encryption. And if you see this right over this, your packet is completely encrypted. You don't see your security association after message 6. And coming back to the ESP tunnel, you can't see any information. If you go to your the best example is we'll do a ping and I'll show you that. As I said before, if you look at this, your ESP tunnel, as I said, your outer header, this guy, 60.0.0.1, and your destination 50.0.0.1. So your source and your destination. This is not encrypted. But your private IP is encrypted. So this outer header is actually used for your routing. So I'll show you one more thing. So let's do ping 1.1.1. Before that, let me go and do a capture for ICMP. Source 3.3.3. Let me do a capture again. I am on R3. Go to capture. Then at 0/1. You can see my ICMP packets. If you actually see without an IPsec tunnel, as I said, this is completely encrypted inside the header. And if you see the data, what is inside, it's completely encrypted. We cannot see any kind of information inside your private IP header. So nobody has an insight about what is exactly inside your packet. All they can see is your outer header. If you see, the communication is happening between 1.1.1 and 3.3.3, but your actual traffic is going over 60.0.0.1 and 50.0.0.1. So other traffic, they are purely encrypted. You can see this encapsulation security payload here. So inside this packet, your actual IP headers are added here. So this comes inside the IPs, private IPs comes inside this. And if you see this internet protocol right over here, the outer header is not encrypted inside the ESP packet. So when you're doing your troubleshooting, you have to check for all these options. And how do I verify that? Show crypto IPsec SA. Okay. Here I got it. I don't know why it's not showing up there. Okay, fine. So if you look at this, uh, my SPI from I'm from R1, right? I'm from R1. So if you see this value, I am on R1, and you can see that my source would be the source is 1.1.1. And if you see my ESP value right over here, E732, it's matching, right? So this is my inbound ESP. My inbound ESP from this guy R1 is E732. So you can see this in the Wireshark, and you can compare this traffic is going from source. When you're troubleshooting, this is very helpful. And coming back to the destination ESP, how do I see the destination ESP packet? I think I have to jump back to the destination. So if you actually go in and check your destination traffic that's coming from 3.3.3, this is a source 3.3.3, but I'll try for it. But this is coming from 5.5.5, so the packet, we are not running a tunnel between we are not running a tunnel between the router 5 and router 3, so the packets we cannot see that. But exactly as I shown you, you have to go back to the router, the destination router, and if you do a packet capture, you can see your actual SPI information. Let's try for that. Let me stop this capture. So I am on R1 now. R1 Ethernet 0/0. Ping 1 dot, sorry, ping 3.3.3, router 3, source, router 1, 1.1.1. I can see the ICMP packets. And from this guy, if you go to the encapsulation header, you can give show crypto IPSec SA. Stop the capture. I'm coming from 1. Okay, here 732. So I am going to this guy. Okay, I am on R1. Okay, this is my source. You can see this SPA values matching here, right? So your SPA values is very important when you're doing your troubleshooting and when you check for your option. You're sending your traffic to the intended destination. That is purely based on your SPA value. can't see your traffic from 3.3.3. So this is how the SPI is used. So when you establish a connection, your SPI value is very important to see your actual traffic is going to the intended destination. A quick rundown about this, what we discussed today. So we discussed about main mode, 1 to 6 messages that is generally happening. So we'll continue the aggressive mode tomorrow, and followed by that, we got one more lab for IPSec with the NAT overlapping. We'll do that tomorrow. But today, the key concentration is for this. So we discussed about, okay, so what if my phase one tunnel is up, and what are the messages, right? So as I said, if your message one fails, then your security association is wrong. And if your message one is up and running, sorry, you can see the successful message one, but if you don't see the message two, then your responder is not actually proposing your HADLE information. And the message three and message four, said it is for your Diffie-Hellman key exchange. Chat secret is exchanged in 3 and 4. Until this point, until message 3 and 4, it is not encrypted. When somebody is asking what is the packet flow between your source and destination for your IPsec, all you have to start with the message one is for the HADLE exchange, happens when the message one from the sender, and the receiver should send the same HADLE information message two, otherwise the message two fails. And if a message one and message two is successful, and I should define the same Diffie-Hellman group on both ends. Only then I can see my message three and message four. That is for security key. Sorry, that is for session key creation. The shared secret key is exchanged between source and destination. So this particular key, right, that is used for session. I mean, so the anti-replay attack cannot happen. Only who has this key can encrypt and decrypt the traffic. So it keeps changing. So that's why you see the idle main mode is actually most of the time it is idle. So once the lifetime is expired, again it goes through the same process. It exchanges your security. So I mean your security parameters, security association parameters, I would say. Then it will go through message 1 to message 6. So message 5 and 6 is completely encrypted. You cannot see anything. The secret message, the session key creation happening in 3 and 4. And if it is exchanged successfully, then your message 5 and 6 is completely encrypted and your phase 1 tunnel is up and running. So if your phase 1 tunnel is up, and if your transform set, the algorithm what we use in the transform set on both, and if it is not matching, your phase 2 may go down. And if you're interesting traffic also, it should match. So when you're doing troubleshooting, if your phase one is up and your phase two is down, you have to look for your routing, then you have to look for your interesting traffic, and you have to check for your transform set is that matching on both ends. So if a phase one and phase two is up and running and you cannot send a traffic, you have to check for your route. Or do I have a route to both my public IP address, and do I have a route in the table for my destination? For your public routing, you should have it. So whenever the best practice is you create a phase one, you create a phase two, and you check for your route. All the three key details are very important to establish your tunnel. We'll look into the overlapping subnet tomorrow. So today the main focus is that. So we saw that a private IP to IP communication is we call this as route based VPN, because we are using the IP to IP communication private subnet 1.1.1 to 3.3.3. That's a subnet we used in our scenario. So tomorrow we see the NAT traversal problems you have, and when we do a NAT and IPsec overlapping, we'll do this two labs tomorrow. And here coming to this and aggressive mode, along with that aggressive mode tomorrow. So here we saw the ISACAM framework. We know what is phase one and phase two now. And we saw the main mode messages, the 6 messages, and the HADLE information. This is actually a HADLE information. And then we saw the quick mode that happens in the 3 messages exchange, and the perfect forward secrecy. We discussed about that. We are using the Diffie-Hellman key in the phase one, so we are not using a PFS. Most of them they don't, but if you want to do that, I think I'll show you. I have that PFS. So if you want to really use it something, your PFS, if you see in the crypto map, you have to create your PFS key. The same Diffie Hellman. So whenever you see the group, that is for Diffie Hellman. So if somebody is asking if you want to use a PFS key, that is used in your, inside your crypto map, you have to define your Diffie Hellman key to create a PFS. That is for your phase two tunnel. Generally, they don't use it because the Diffie-Hellman consumes a lot of compute power. So the phase one, we are actually using the phase one Diffie-Hellman key for encrypting the traffic in the session. So if you want to really do it, then you can go ahead and do it in your crypto map. You can create your key, perfect forward secrecy key. And as I said in the show crypto IPSec essay, if you give it, if you see this PFS, then your Diffie-Hellman algorithm should be enabled there. But we are using the Diffie-Hellman group key creation only in the phase one. So we see that Diffie-Hellman group was no. But if you created a PFS on the phase two, you see that yes option. If you have actually enabled right over here in the crypto map. So verify if a PFS is used, you can use show crypto IPSec as a command, and if you give include PFS, you can see that. So here they are telling the difference between group 1, 2, and 5 that uses the highest Diffie-Hellman group. So we use Diffie-Hellman group 2. So we use this 1024-bit encryption for it. So this is really about the IPSec, every packet. So you have to explain someone in a sequence. You should not, explain something like bits and pieces. As I said, like a step by step, phase one, HADLE information, phase two, transform set, interesting traffic, apply it on your, create a crypto map and apply the crypto map on the interfaces. Then you can establish your connection. Show crypto ISACamp SE is the first command to check your all your security association should match, and you should establish a connection. Without that, you cannot troubleshoot your phase two tunnel. Your phase one tunnel should be up and running. It should be quick mode idle state. It's in sleeping state. Once your session expires, it creates a new key. So then you have to go to your phase two. There you can see your transform set. And as I said, you can see your inbound SPI and you can see your outbound SPI. You can see your interesting traffic inside the ACL, and you should have a return route as well as your route to the destination from source route, and the return route both should be in place for your complete encryption and decryption. And as I said, in the inside your ESP header, you can see only the new header information that's for your outer IP, your public IP address actually used for routing, and all the further data payload is encrypted inside your ESP. And the protocol used is protocol number 50. And this IPsec tunnel is using the ESP as a transport for the communication. It is not using TCP or UDP. It is using its own protocol that is called ESP, encryption security payload. That's how it sends the traffic back and forth. So that's it really about the IPsec. Now let me stop recording again. If you guys have any questions, you can ask me. There's a lot of background noise, Akbar. I don't know, it's coming from Vishal or Akbar.
No, wait. No.
Hi, Akbar, do you have any question?
My friend. Praveen.
Yeah.
Vishal Praveen. He's been working with you or something?
Akbar, actually, your voice is, a lot of echo coming in. Can you, yeah. Hello. Hi, Akbar. I can't hear you. Maybe.
Hello, sir.
Hello. Yeah.
Hello, this is Akbar. Sorry, we are having some work here.
Mm-hmm. Okay.
Hello, sir.
Yeah, yeah, I can hear you, Akbar. I can
Because
hear you.
today I was in my work site, so I could
Hmm.
not attend your session. I joined last time.
Okay, no problem.
Sorry, okay. Because did you search about the NAT NV and virtual interface?
Yeah, yeah. When I am creating the natting, yes, it's
Okay.
virtual
I think
interface is
in today's
created.
session you did not discuss about the NAT T, right?
Yeah, yeah. Tomorrow we'll do a nat.
Tomorrow, because okay. Today, please, if you can please upload the session little bit early, by Saudi time, 2 o'clock or something like that.
Okay, yeah, I'll talk to the team.
Okay, sir.
Yeah.
Thank because I could not attend because I was on our site. We are
Uh-huh.
upgrading some server and these stuffs.
Okay, okay, no problem, no
Okay,
problem.
sir. Thank you very much.
No problem. Thank you. Yeah. Any other questions, guys? No questions about IPsec?
Yeah, nothing from my side. It's clear.
Okay, cool. Um, Mario, you're good?
Yes, actually, one rapid question is if the PSC
Mm-hmm.
um, is the
PFS.
same. Yes, is the same, is an identificative number, and is the same from between the neighbor. Is share between the neighbor and identify the session.
You mean to say the PFS? Pub,
No, I mean the sorry, the SPI security
security parameter.
security parameter index. Yeah, sorry.
Yeah, yeah. So what is the question?
Yeah, is a identificative number for the session. So is the same in one side and in the other side for the session. When you
I mean,
see
it's an
when you make it,
unique. It's a unique number, and the sender and receiver should have a different SPI,
they have a different one.
different security parameter index. Yeah, that's how
Okay,
we differentiate the traffic. So when you see that when the initiator is sending the information with SPI, and if you don't
Mm.
see the responder is not sending any SPI information, it means that it is not ready to propose its haggle information. You should see that
Okay,
SPI coming in, and it's a unique number for the source and destination, or maybe your sender and the responder.
okay.
It's a
So,
unique
but
number.
from a troubleshooting point of view, on different routers, you should see different
SPI number.
numbers.
Yes, yes, yes. Correct. If you create the other tunnel, then your sender and receiver SPI are different. So it's a unique number for every IPsec tunnel creation.
So, is a unique number for every tunnel.
Every tunnel, yes. It is not
So,
same.
So
Yeah.
why is not the same? If identify the tunnel between, for example, router one and router three, if identify that tunnel that is built in that moment, why is not why I don't see the same if I capture a packet on router three and router one? I mean, if it is an identificative number, I expect to be the same for that tunnel for that moment.
Tunnel that moment, and if it is expires only, then your new SPI is created on both sender and receiver.
Okay, okay,
Yeah.
okay, okay. Thank you. That was the question. Thank you.
No problem. Yeah. So Deepa, you're good. Raju.
Hello?
Yeah, yeah.
Yeah, it is good from my side.
Yeah, okay, okay, cool. So Raju, you're clear.
I'm good, sir.
Thank you. So Suresh, you're good. Okay. Hi, Vishal, you're good. Okay. So if you guys have any further questions, you can let me know in the next class. So until then, we'll see meet tomorrow. So good night, bye, and let's see tomorrow.